Welcome to Week 4 of Inquiry Science, Hypothesis Testing. This week we'll explore the question, how can we support bilingual learners as they make plans to test a scientific hypothesis? During this week's learning, we will explore the different steps of hypothesis testing. We'll cover writing justified hypotheses, then move to the preparation for experimentation, deciding what data to collect, writing a procedure, and listing materials. This phase of inquiry works best when it comes after an initial launch, discussed in Week 2, followed by generating a testable question, discussed in Week 3. As we talk about these science inquiry steps, we will discuss several strategies that will help bilingual learners get the biggest language gains from the inquiry experience. In particular, we'll discuss using a gradual release model, leveraging bilingual assets during cooperative learning, and using visual aids. Let's begin by discussing the first step in this week's science inquiry phase, writing a justified hypothesis. This can be simple or more involved, depending on the time demands of the class. In its most simple form, a hypothesis is a possible answer to the testable question. In its most complex form, a hypothesis links different models of the way the world works to possible experimental results. Let's take a look at some examples, both basic and advanced, in the context of an inquiry investigation about what causes a stream of water to meander. Students can take a testable question about whether the smoothness of the surface of the board affects the size of the meanders, and turn it into a basic hypothesis. Changing the smoothness of a board will affect the size of the meanders. Right or wrong, this is a great basic hypothesis. Teachers can probe further to determine the reasoning behind students' answers. This leads to a more advanced, justified hypothesis. A student might suggest that the stream of water is getting slowed down by the board's surface and piling up in loops or meanders. With the right support, including sentence frames, students may write justified hypotheses, such as the one shown here. If the rough surface of the board is causing the meandering, then making the surface more smooth will decrease the size of the meander. Again, this hypothesis may not be correct, and that's okay. A hypothesis may be the most misunderstood part of science instruction, leading students to think that their experiment should prove the hypothesis to be correct. It is critical that teachers reinforce the idea that when you can prove your hypothesis to be incorrect, this is a great success. It forces us to create newer and better models. The only disappointing outcome is a result that doesn't provide evidence either in support or against the model. If it's to be a useful part of the process, making a hypothesis should make students think deeply about their own model of how things work, considering how different possible outcomes of an experiment might support or disrupt their model. For bilingual students to talk about how things work, the draw talk strategies from Week 1's Explore will be very useful. Once the students have a justified hypothesis or a basic hypothesis, we're on to step 2, making a plan for data. They need to decide what to measure and record, decide how many times to repeat, and design a data table. Most science lab books provide data tables and detailed instructions for students about what data to collect. But there's no reason not to demand more of our students, provided the support exists to ensure success. This epitomizes what research describes as one of the most effective classroom environments for minority students: high demand with high help. It's a worthy goal to demand that every student be able to design an effective data table. But first, let's examine the support needed to ensure success. Many teachers are familiar with the modeling technique of I do, we do, you do. This is an appropriate scaffold for making a data table and other elements of the inquiry process. First, the teacher models both the internal thought and the external action that happens when we make a plan for data. Second, the teacher begins to involve the class in the process, asking questions, calling on students, and co-constructing a plan. We do. Finally, the teacher releases the task to the students. All students, especially bilingual students, will benefit from collaborating with peers, getting additional support with this peer-to-peer communication. A you do in groups can be a very important support, but it should not replace the demand for eventual independence with the task. The final you do is equally important. A few questions aid students in the decision-making process. What will you observe? What will you measure or count? How many trials or how many times should we repeat with each change? In a gradual release approach, the teacher might ask these questions during the first few experiments of the year, describing their thinking as they construct their own plan. This would be called I do. After the initial modeling, the class can answer these questions together. We do. In subsequent experiments, the you do portion of gradual release can be done in groups with some peer-to-peer support before students are asked to perform the task individually. After we have a plan for what data to collect, we're ready to write a procedure. Teachers can ask students questions to make their procedures more detailed. Is it step-by-step? Does it control some of the variables that might affect the results? Is it likely to answer your testable question? The exercise of writing a procedure is an excellent way for all learners to practice sequential writing, an essential component of literacy. Making the connections between science and literacy will deepen student learning in both areas. With a gradual release approach, a teacher models writing a procedure, practices it as a class, and then releases the task to student groups before students attempt the task individually. A process of drafting and revising is encouraged. Also, encourage students to draw and label diagrams to make their procedure clear. A proficient example will help all students, but this is still a complex task with high language demands. Next, we'll look at strategies we can use to help bilinguals in this task. For some students, a procedure may take the form of numbered diagrams, similar to the draw-talk strategy used to explain students. All students will benefit from creating their own labeled diagrams, but this will be a great resource for bilinguals and a great resource for a teacher-student dialogue. Note that once a diagram is drawn, labels can be added in a way that connects the word to a real-world association. This is perfect for learning science vocabulary. Recognize that while the needs of bilingual students may be different from their monolingual peers, they also have strong assets that can be leveraged during this creative and collaborative task of writing a procedure. Carefully controlled studies of bilingualism point to significant advantages, including an increase in the flexibility of thought. Many, but not all bilingual students come to school with a set of cultural norms that are significantly more collectivist in nature. This is perfect for a complex task like writing a procedure. Recognizing assets may not sound like a strategy to help bilingual students in science, but mere recognition makes teachers better able to help students successfully navigate a challenging task. Along with writing a procedure, students should eventually be able to make their own materials list. The teacher's job as a content expert is to decide the right level of support. Students might need suggestions for new ways of measuring, with demonstrations if you're suggesting a method not already used during the initial observation experience. They might need help learning or remembering the names of pieces of equipment. They might also need help identifying the limits of what they can and can't do. This leads to our third language strategy for bilingual learners, visual aids. Visual aids will greatly assist students during this phase of inquiry, helping them build science vocabulary. These aids can be charts, word walls, or labels. If we lower the demands of the task by providing a set of materials for the students and showing them what to do, we also limit the chances for students to use new words and acquire new academic vocabulary. We want students to be asking themselves, what was that thing called? And using an appropriate resource like a word wall to figure it out. When bilingual students are asked to make their own decisions about materials, and when they have to write and say the materials needed to complete an experiment, this is the perfect opportunity for language acquisition. During this video launch of Week 4, we've explored how to help students create 4 things needed to begin experimenting: a hypothesis, a data table, a procedure, and a materials list. To add support for bilingual learners, we acknowledge and leverage bilingual students' assets, we use visual aids, and we utilize teaching strategies such as the I do, we do, you do gradual release. Once student groups develop some independence with science inquiry, these 4 tasks can be presented as a checklist of prerequisites that are part of an experimental plan. For greater rigor, teachers will give feedback to groups and require revisions before approving their plan and letting them begin their experiment. One final note before you begin your own Explore. Allow us to thank you for the work you do every day in the classroom. Facilitating student-led hypothesis testing isn't easy. It takes significant preparation, organization, and thought. Most importantly, we hope you recognize all the ways that science inquiry benefits your bilingual students. They get to practice academic ways of speaking in cooperative groups. They use academic vocabulary and context. They benefit from a host of non-linguistic representations, including measurements, diagrams, and graphs. They can participate in work with a high cognitive challenge, and they can produce lots of authentic writing based on their own observations and thoughts. For this work, thank you.